Good morning, everyone. This is our last day, and I'm very happy to introduce our last invited speaker for AISTATS, Tamara Broderick. She is an associate professor in the Department of Electrical Engineering and Computer Science at MIT. She finished her PhD in statistics at UC Berkeley, and she has many degrees. She received her AB in math from Princeton before PhD, and then a Master of Advanced Study for completion of Part 3 of the Mathematical Tripos from the University of Cambridge, an MPhil by Research in Physics from the University of Cambridge, and MS in Computer Science from UC Berkeley. She has focused her research in scalable Bayesian inference and also Bayesian machine learning, and then she has also many awards. She has been awarded from the Office of Naval Research an AISTATS notable paper in 2019, so it's good to have her back. And then an NSF career in 2018, a Sloan Research Fellowship, an Army Research Office Young Investigator Award, Google Faculty Research Award, an Amazon Research Award, an ISBA Lifetime Members Junior Researcher Award, the Savage Award, just several awards, Berkeley Fellowship, an NSF Graduate Research Fellowship, a Marshall Fellowship, and also the Phi Beta Kappa Prize for graduating Princeton senior with the highest academic average. So with that, we're so happy and privileged to have Tamara today to talk about robustness of finite sample.
Yeah, thanks so much for the super generous introduction. Thanks to everybody who woke up early this morning to come to this talk. It's great to be here. So today I'm going to be talking about a check that you can run on your data analysis, namely a check to see if there exists a very tiny fraction of data that if you dropped it would change the substantive conclusions of your analysis. Now, before I go on, I want to highlight the amazing work of my fantastic postdoc, Ryan Giordano. He's about to start a faculty position at UC Berkeley. And our awesome collaborator, Rachel Meager, who's a professor at the London School of Economics, and definitely the economics expert on the applications that I'll be talking about today. Okay, so at a super high level, this talk is addressing when can I trust decisions that I'm making from data. So of course, the promise of our field, in some sense, is that as we get more data and better computation, as we have over the past few decades, we're increasingly able to make life-changing decisions with data. This could be in individual medical care, it could be in individual finance or financial policy writ large, it could be in education. The point is these are applications that really matter, and we really want to get them right. So we probably want to check our data analysis in a variety of ways. Now, I want to emphasize today I'm not going to try to be exhaustive and say here are all the checks that you should run on a data analysis. Rather, I want to suggest a check that I think will be pretty widely useful. And this is very much motivated by the observation that typically when we're using data to make decisions, we first run a data analysis on a set of available data, but the goal is always to apply those decisions at some point in the future. So an example of this that we're going to see a lot today, economists are interested in the effect of microcredit. These small loans to individuals in impoverished areas, and the hope is that it's going to help raise them out of poverty. So they run some randomized controlled trials of microcredit, but necessarily the goal is always to apply microcredit at least in the future, and often at a different location than they've already seen. And so here we're taking a generalization step. We're generalizing from the data that we've seen to new future data. And I want to suggest that we might worry about that generalization step if it turned out that an extremely small subset of our data was absolutely instrumental to the original conclusion. So let me give you an illustrative example that we're going to see in a lot more detail later. In a real-life randomized controlled trial of microcredit, with over 16,500 data points, which is a lot of data points for the amount of effort that goes into collecting this data, we find that we can drop a single data point from the data set, rerun the analysis, and change the conclusion. That is the difference between microcredit helping people and microcredit hurting people. So hopefully, if you've run data analyses, which I think everybody in this room has, this is worrying. You're worried that somehow these results are brittle because they seem to really depend on this one data point. And hopefully you feel a little bit motivated to understand, hey, if I have a new data analysis, is it going to have this problem? Is it going to have this issue that a very, very, very tiny fraction of my data could be dropped and change my substantive conclusions? And so the reason that we have a talk today is that this is computationally challenging. We can't just brute force our way to success. We're going to get into this more in detail later, but it's just astronomically costly to actually check every tiny data subset. And so we're going to see that an approximation instead is fast in user time, it's automatable, and it's accurate. In fact, we're going to see that you don't even have to trust our theory. You can check it directly yourself at minimal cost. And finally, we give an empirical and theoretical analysis of how this sensitivity, and in particular, how this sensitivity approximation behaves in practice. Okay, so let's go ahead and launch in this talk today. First, I'm going to go into a little bit more detail about why do we care about this worst case dropped data subset. How would we like to find this worst case dropped data subset if we had infinite computational power? But of course, we don't have that infinite computational power. And so we're going to see why is this just so computationally expensive. We'll see that we have an approximation that will be fast and again, automatic. So fast not just in compute time, but in user time. And we're going to see that using this type of robustness, many analyses are robust, but some are not. Also, very importantly, this isn't something that you could get immediately from existing tools. You can't just check for gross outliers to see if you have this type of robustness. You can't just check to see if you have a large p-value. You are probably familiar with other types of robustness, like Huber robustness or epsilon contamination. If you are, I will suggest, and we will get into more details later, that this is not the same thing, that it's not just a product of heavy tails or similar things. In fact, we'll hopefully get a little bit of an intuition about what's really going on in this type of robustness, that it's reflecting a notion of signal to noise. So for the moment, signal being sort of what we want to find out about our data, and noise being the thing that's making that hard. And we'll firm up those concepts later on. Okay, so let's dig into why do we want to find this worst case subset that if we dropped it would change our conclusions. Okay, so first observation here is that often when we talk about sensitivity or robustness, it's as though they're monoliths. We just say sensitivity, robustness. But of course, we really always mean that as shorthand. We really mean sensitivity to some change, robustness to some change. And so, if we had an analysis that literally never changed, no matter how we changed our data, that would not be a useful analysis. So of course, what we really want to ask is not, is our analysis sensitive, but what types of sensitivity are concerning to us, are worrying to us? And of course, that's got to vary by problem. I think you probably have a lot of types of sensitivity that are concerning to you in any given analysis. So again, I'm not trying today to say, hey, here's the type of sensitivity you should always be concerned about, or the best type of sensitivity. Rather, I'm trying to say, here's a type of sensitivity you should often be concerned about. Now, throughout the talk today, we're going to look at economics. Why economics? One, it's got super important applications that affect really all of our day-to-day lives. Two, my goodness, is this a wonderfully reproducible field? I cannot emphasize that enough, how awesome it is. And three, we got to collaborate with this wonderful economics expert, Rachel Meeker. Okay, so just as a little bit of a motivating example, that's not illustrative of everything that we're going to find, but I think gets us started. Let's dig into this microcredit example a little bit more. So what's happening in microcredit? Well, economists run their randomized controlled trial. They randomly assign villages to either receive microcredit or to not receive microcredit. And so let's look at our village that received microcredit and our village that did not receive microcredit. Now, economists will measure something that they can, like perhaps business profit of all the small businesses in the village. And typically, the way that they'll compare things is they'll take a mean. They'll say, what is the mean business profit of the village that received microcredit? What is the mean business profit in the village that did not receive microcredit? Well, so we can get some sort of situation, like let's say the CEOs of Amazon and Facebook and Google walk into our village, and beforehand, the mean business profit in both villages maybe looked like this, and suddenly the mean business profit in the village that received microcredit is just through the roof. It's because as soon as you have somebody with a large mean business or a large business profit, it's just going to completely affect the mean and go crazy. Now, of course, this is a cartoon. We'd like to remove these CEOs and just sort of understand what's the mean business profit without them. But of course, we don't really expect CEOs to walk into our village. What actually is very realistic, though, is that a very few people are actually affected by microcredit, and other people may not be. In which case, we don't necessarily expect to see those same few people in the future, and we might worry again about this notion of generalization. And we might want to pick them out and see what happens without them. Okay, so standard tools are really meant to address this notion of generalization. Things like p-values and standard errors. The whole point, in some sense, or the way that they're often used, is to understand, hey, I have this particular sample, but is my lesson from the sample going to apply in the future? But the problem is that typically they make a lot of assumptions that we know aren't realistic in these real data analyses. So of course, the first big one is this assumption that my test data is IID from the same population as what I'll look at in the future. And we just know that that's not the case. The population where we apply policy in the future is necessarily going to be systematically different from the population where we actually run our data analysis. At the very least, time has passed, but it's often a different village, a different location entirely, in this microcredit example. Now, of course, we hope that the deviation from IID sampling is very small, that it's not really affecting our conclusions, but it would be great to check for that type of sensitivity, and that's what we're trying to get at with dropping a small fraction of data. These methods also typically assume that our model is correct. And again, we know that that's not true. We know that all models are wrong, that all models are misspecified. And so again, we might worry that we can't just rely on these traditional statistical methods. Traditional methods assume that the output is what we want. We heard from Shakir's talk yesterday that we know that often that's not true. And certainly in this case, we're reporting a convenient proxy in my example. When we look at the mean business profit, that's not what we care about. We really care about that a lot of people, especially a lot of poorer individuals, are benefiting from microcredit. And so again, we might worry about brittleness and dependence on just a few data points. And of course, in the social sciences, we often have data missingness. When we have data missingness, we will assume typically in typical methods that it's at random, but in reality, it's typically not at random. And so again, we might worry that our analysis depends on a very small fraction of data missing not at random, and we might want to check that directly. So in all of these cases, we'd be concerned if dropping a tiny fraction of data revealed brittleness in our results, if it changed our conclusions. And I really want to emphasize that these concerns are very much not specific to economics. When we're doing science, when we're doing social science, we're trying to make generalizations about the world. We're trying to find out fundamental things about the world, not about this particular population that we're measuring at one particular time. We are always having an incorrect model. We know that models are misspecified. The output is often a convenient proxy because we're using standard statistical tools. People aren't necessarily developing a new tool every time a new problem comes along. The missingness data, of course, only applies to certain problems, but it does apply to a good number of problems in the social sciences and medicine, for instance. Okay, finally, I do want to say a counterexample for when you don't want to care about this. So for instance, imagine that I'm measuring some kind of really rare event. Like maybe I have 100,000 people in this village and 100,000 people in this city and 100,000 people in this other city, and maybe I'm measuring some rare crime. So maybe there are 6 instances in this city and 3 instances in this city. And I want to compare the cities for this crime. Now in this case, I wouldn't want to remove the worst case dropping data subset because I could just remove all of the rare crimes. But conversely, I should probably be upfront that really, at the end of the day, I don't have 200,000 data points for comparing these rare crimes. I have 6 versus 3. I have like 9 data points. Okay, so even if this doesn't bother you, we should just make sure to be upfront about what we're trying to do and how much data we have. But hopefully at this point you have a sense that many times we care about dropping a small subset of data and how it affects our analysis. And so now let's think about how we'd like to do that. So as we said, we might worry if dropping a very small fraction of data changed your decision. So let's start to introduce some notation. Let's let alpha be that fraction. So it's between 0 and 1. And remember, we're really worried when alpha is small. Eventually we think if we keep dropping data, we should get a change. So it's only worrisome it's a very small fraction of data. So what does it mean to change our decision? Well, it depends on what we're using to make our decision. So I'm just going to give some examples, but they're certainly not exhaustive. An economist might say, hey, maybe I'm going to invest in microcredit if I estimate the effect of microcredit and it's positive. So I'm going to estimate based on, or I'm going to make my decision based on the sign. Maybe I'm going to invest in microcredit if the effect of microcredit is statistically significant, in which case I'm making my decision based on something like our estimate plus or minus 2 standard errors. Maybe I'll change my decision if I can change it not only to a different sign, but a statistically significant result of the opposite sign. So these are just some examples, certainly not exhaustive. Okay, so with the idea of decision-making in mind, that we're using our analyses to make decisions, let's define now what we're going to call the maximum influence perturbation. This is the largest possible change we can get in our quantity of interest by dropping our alpha fraction of data. So for instance, let's say we were making our decision based on the sign. Well, what's the biggest change in the effect size we can get by dropping a very small fraction of data? If it's so big that we can change the sign, then we're worried. If it's not, then we're not worried. Now, if it turns out we can drop an extremely tiny fraction of data and change our decision, we probably want to know what are those data points so we can analyze them more, we can dig in and see what happened. So we're going to call that the most influential set. What's the data that we dropped to achieve this maximum influence perturbation? Okay, so on the face of this should be, at least, thinking about it, straightforward to calculate. Just take every tiny data subset, drop it, and then ask, did we change our decision? By rerunning the analysis. So that's just a brute force computation. So let's see what might go wrong there. So we already talked about a data set that has over 16,000 data points. So let's suppose we have 16,000 data points. And let's suppose that we decided we would be concerned if we could drop 0.1% of our data, a very small fraction, and change our substantive conclusions. So here alpha is 0.001 as a result. Well, we want to look at dropping every data set of size 16 and probably 15 and 14, et cetera. Let's just look at dropping all the data sets of size 16. A data set of size 16,000 has about 10 to the 53 different subsets of size 16. I think you all have experienced running data analyses that take more than 1 second, but let's be optimistic and suppose that our data analysis takes just 1 second to run. In that case, this check takes over 10 to the 46 years. So there's a lot of problems these days that parallel computing can really help with. And in this case, this is just not one of them. Parallel computing is not going to save you. You could have all of the compute of the major tech companies, and you're not going to solve this simple economics problem. Okay, so we're going to need some kind of approximation. And so before I tell you what that approximation actually is, let's see it in practice on a real data problem. And in fact, this is a microcredit problem. So this is Angelucci et al., 2015. There are actually 7 very famous randomized controlled trials of microcredit. This happens to be the largest of them with over 16,000 data points. I'm calling these households here for the purposes of going forward. You can also think of them as small businesses. I can't emphasize enough the fantastic reproducibility and data sharing of the economics field. It's really great and allowed us to do our analyses here. Now, it turns out economists look at various models here, certainly some more involved than the one I'm about to show you, but let's stick to the simple stuff where we have a lot of intuition. We can start with a really super simple linear model here. If linear models can be non-robust, then surely more complex models can be non-robust. So here, n is going to index our small businesses. Xn, our single feature, is going to be a microcredit indicator. So it's 1 if this small business received microcredit, it's 0 if not. Yn is the observed business profit for this small business. And theta naught and theta 1 are the parameters, the unknowns of the model that we want to solve for. So theta naught's like, what would be the business profit if microcredit didn't exist? And theta 1's the effect of microcredit. If it's positive, microcredit is helping business profit. If it's negative, microcredit is hurting business profit. And that's the thing that people really care about in this analysis. Now, it turns out in the original analysis, and we can reproduce this pretty much exactly, theta 1 hat is negative 4.55 US dollars purchasing power parity every 2 weeks with a standard error of 5.88. And so based on this, you're probably not going to invest in microcredit. It's also worth noting, though, that it's not a statistically significant result, that negative is within the standard error. Okay, so we can run our approximation. It takes 2 seconds to run, not 10 to the 46 years, so this is going to be practical. I said earlier that we could remove one household and change the sign of the effect, in this case to negative to positive, but you're probably thinking, hey, but it wasn't statistically significant to begin with, so that doesn't necessarily change my final conclusions. And I think something that certainly does change a final conclusion here is we can drop 15 data points, that's still less than 0.1% of the entire data set, and get a statistically significant result of the opposite sign. So here theta 1 hat is more than 2 standard errors away from 0. Suggesting that this is a pretty brittle analysis on the face of it, and we'd like to really understand what's going on here. Okay, I haven't told you the approximation, so something you could very reasonably be thinking right now is, yeah, you told me some numbers, but maybe they're made up by your approximation and aren't really what happens when I drop data. And so the important point about our method is that we tell you the problematic data points. And so at the cost of just one extra data analysis, you can just drop those data points, rerun the analysis, and check, did you get the promised change? And in this case, that's actually what we do. In fact, we do that in all of our experiments. And we find that this is indeed the change that we get. Now, you also might be thinking at this point, gosh, this wasn't a statistically significant result to begin with, and that's the real problem here. And we're going to see later that that's not the case, that we can start from a statistically significant result in a real major economic study and change that by dropping a very small fraction of data. You might be thinking, hey, the problem is gross outliers. You know, we could have just gotten rid of gross outliers and not had this problem, and we're going to see that indeed that is not decisive, that in fact in analyses where people got rid of gross outliers to begin with, you can still have this sensitivity. Again, you might be thinking of other types of robustness. You might be thinking, hey, the problem here is heavy tails, or that you're reporting means, and we're going to see also that is not decisive. That's a different type of robustness, not the one that we're seeing here. You might be thinking, man, if only you used a Bayesian model, you wouldn't have this problem. We're going to see that, in fact, you can totally have this problem with Bayesian modeling and inference. Okay. Hopefully, we'll get a sense as we go along that what this is really reflecting, this notion, the sensitivity to dropping a small fraction of data, is a notion of signal to noise in the data. And we'll get some intuition for that. Okay, so at this point, we've talked about why do we care about this sensitivity to dropping a small fraction of data. We talked about how we'd like to drop data if we had infinite computational power, and in fact, we don't. And so we saw that this was actually way too computationally expensive to use the brute force method. And so now we've seen this approximation in action, but let's spend a little time saying what this approximation actually is. Okay, before I do that, let's just look at a pretty generic looking data analysis so we can play with it later. So we'll have a bunch of data. So N here is indexing our data points like before. Our data points could be a set of features and a response label like we had before. So some XN vector maybe and some YN, but it doesn't have to be. We could be doing semi-supervised learning. We could be doing unsupervised learning. We just have a pretty generic set of data points here. We have a set of parameters, the unknowns that we're interested in learning here. We have some loss that relates our parameters to our data. We might sum up our losses up to capital N data points, and perhaps we even have a penalty or a regularizer. Now, a typical thing that we might do to estimate theta is minimize our regularized loss, and we get our estimator theta hat. Okay, a lot of stuff fits into this framework. Obviously, any kind of regularized loss fits into this framework, but some examples of this are an MLE, you could have a negative log likelihood for that F. A map, you could have a negative log prior for that R. Variational Bayes actually fits into this framework. And it turns out that our method actually works much more generally than even this framework. So actually any Z estimator works where you have an estimating equation and set it to 0. For instance, by taking a derivative here and setting it to 0 to get the minimum. So of course, again, we get MLE, map, BB, but we also get anything that has this general form. And so 2 talks ago from Arthur, we heard about things like instrumental variables regression, where we might have sort of multi-stage analysis. That'll fit into this too. Okay, but let's stick with this data analysis for the moment because I think it's pretty accessible and familiar to people. Now, we saw in the microcredit analysis that that's not where things end in real life. We don't just estimate the parameter and call it a day. We actually now use something about that parameter to make an actual decision, to make an actual policy based on our data. And so let's call this thing that we're taking from the parameter the quantity of interest, the thing that we use to make our decision. So just some examples. In the case of microcredit, what we did was we sort of ignored theta naught after we estimated, and we picked out just theta 1. And so we could just pick out a particular element of theta hat, for instance, to look at its sign. If we care about statistical significance, we might look at that element plus or minus 2 standard errors. We don't have to be frequentist. We could take a posterior mean or a posterior credible interval endpoint. All of these could be our quantities of interest. These are just some examples. Okay, so everything up to here on this slide should be review from your classes. And now we're going to start tweaking things a little bit. We're going to give every data point a weight. So data point 1 gets a weight W1, data point 2 gets a weight W2, up to data point W capital N, or data point N and W capital N. And in our original analysis, we can think of all of our data points as getting a weight of size 1, which we can collect in the all ones vector 1 subcapital N. And now we can conceptualize dropping data as taking some of these weights from 1 to 0. So if we drop the 10th data point, we take W10 from 1 to 0. If we drop the 10th and 11th data point, we take W10 and W11 from 1 to 0. And so hopefully you agree with me that every drop data subset corresponds to a different weight vector W. So now let's look at how does this change our analysis up at the top. Well, basically, we're going to pre-multiply each of our losses by the corresponding weight. And so let's think about why does this make sense? Well, if my weight is 1 for a data point, it's still included, so I include its corresponding loss term. If my weight is 0 for a data point, we're throwing it out, and so I get rid of its corresponding loss term. And so now implicitly, theta hat is in fact a function of W, so let's make that explicit. And phi, in turn, is going to be a function of W, if only because it's a function of theta hat, but also it could actually be a function of W in other ways, for instance, in a standard error. So now we're going to make this observation. Remember, we only care about the case where we take W very close to the all ones vector, where we've dropped a very small fraction of data. So a very small number of elements of W have become 0. And so maybe we think, because W is so close to the all ones vector in the cases we care about, that a Taylor expansion in W would be an acceptable approximation. Literally, that is the approximation. In fact, it's the simplest possible non-trivial Taylor expansion. It's just going to be a first-order Taylor expansion. That's it. But let's go ahead and write this out. Okay, so here I have my generic-looking data analysis from the previous slide. I've just repeated it. I have my example quantity of interest from the previous slide that's just repeated. And now we're going to write out our first-order Taylor expansion around W equal to the all ones vector. Remember, that's just our original data analysis with all the data. Okay, let me walk you through this. So first, we have phi of W. Remember, every W corresponds to a drop data subset. So we've got like 10 to the 53 of these. We wish we could run our data analysis to get all 10 to the 53 different phi of W, but that's totally impossible. And so we're going to need an approximation. And so our approximation is going to be this linear approximation. So we'll call it phi super lin. It's linear because it's just a first-order Taylor expansion in W. So what is that? Well, first we have the 0th order term. That's phi of the all ones vector. So that's just our original data analysis. You got to run at least one data analysis. Then we have, then we have the linear term. So this is basically a dot product between the W vector minus the 1 vector and a vector of first derivatives. So these are just the first derivatives of phi with respect to W evaluated at the all ones vector. This just comes straight out of writing a Taylor expansion. If you're familiar with influence functions, you might recognize this as the influence score of the nth data point. If you're not, don't worry, it's still a first-order Taylor expansion. Now, a question that we should have at this point is, can we compute this? So surely we can compute phi of the all ones vector. That's what we get from our original data analysis. We can compute W minus 1. But it's not immediately obvious that we can compute this influence score. Luckily, like so many great ideas in the world, all the work was done for us in the 60s. Thanks, statisticians. So basically, the influence score can be rewritten with the implicit function theorem and the chain rule to get just a nice little formula that ends up being things like the derivative of f with respect to theta. Now, back in the 60s, people were like, man, there's no way I'm actually going to write these derivatives down by hand. Sometimes it's going to be just super hard to figure them out. And luckily, nowadays, we have automatic differentiation tools that are just built into all of our statistical and machine learning software. And so that's super easy to actually calculate. And so the point here is that the user doesn't need to do anything to compute this. They need to specify their loss, and they need to specify their data, but beyond that, everything else can be automated. Now, I want to point out that many authors have approximated or suggested removing data points in some form using an influence function, but for very different purposes. So for instance, again, back in the 70s, people have thought about removing data points and approximating that with an influence function to debias an estimator. That was a very popular thing to be doing back in the day. More recently, in the machine learning literature, people have thought about removing data points and approximating that with an influence function as an interpretability type of analysis for a black box method. We've actually done some work, along with a number of others now, in approximating cross-validation. You can think of cross-validation as dropping some data. If you have a fold of cross-validation, you're dropping a little data. You can approximate that. But to the best of our knowledge, nobody suggested this maximum influence perturbation, this notion of finding this worst-case dropping data fraction and then analyzing it both theoretically, or either theoretically or empirically. So that's what we're focusing on here. Also note this can be seen as a special case of a breakdown point or local robustness. So in the sense of it is a point where your analysis breaks down. But typically the breakdown point literature has really focused on, if I can change a data point an arbitrary amount, well, can I change my estimator an arbitrary amount? And we're not focused on sort of either of those directions. Also in local robustness, we've done some work before looking at things like, hey, if I change my likelihood a little bit or my prior a little bit, does that change my substantive conclusions of my analysis? But here we're looking at this data problem instead. You might also be thinking, hey, you don't have to stop at a first-order Taylor expansion. How about you keep going? And in fact, that can be really useful for approximating other things like the bootstrap. But in this particular case, it turns out it's super important that we stopped at a first-order Taylor expansion, and that's because we're not done yet. So we took our 10 to the 53 different data analyses and replaced them with one data analysis. Now we just have to do the phi of the all ones vector that we get from our original data analysis. But if you look at this slide, it looks like we have to make our linear approximation 10 to the 53 times. And that's still too much computation. In fact, we don't want to do 10 to the 53 additions. And so we need to get away from that. And so we need just a little bit more development to get to that point. So in particular, let's just revisit. So here we just have the top of the previous slide. Let's just revisit, what are we trying to do at the end of the day? We're trying to say, what is the worst case change that we can get by dropping a very small fraction of data? So we want to find the worst case, the biggest, phi of w minus phi of the all ones vector. Now you'll notice I've chosen a particular direction here. That's without loss of generality. If I wanted the other direction, I'll just take negative phi. But I want to find the biggest change, phi of w minus phi of the all ones vector. Now, of course, I can't do that. I can't run these 10 to the 53 different data analyses. And so I'm going to find the worst case approximate change, the biggest difference between our linear approximation at a small drop data subset and the all ones vector, the original analysis. But this is easy to write out because we're just going to use our equation up above. We're just going to take phi of the all ones vector, put it on the other side. So we're left with the linear term in the Taylor expansion. Now, there's two possibilities here. Either Wn is equal to 1, in which case the corresponding term disappears, or Wn is equal to 0, in which case we get negative of the influence score. And this suggests an algorithm. The algorithm is as follows. 1, compute all of the influence scores. There's one of them for every data point, so this is going to be a linear time step in the algorithm. 2, sort the influence scores. This is going to be an n log n step. In all of the analyses I'm talking about today, sort is definitely not the bottleneck. If sort is the bottleneck in your analysis, I would love to hear from you. That sounds really, really cool. But for the moment, we're going to say that n log n is a totally acceptable computational complexity, certainly it's much, much better than the combinatorial stuff we started with. Okay, finally, we're going to remove the largest influence scores. So first, let's start by removing the absolute largest influence score. Now we have the biggest approximate change that we can get in our quantity of interest. Now let's remove the second largest influence score. Now we have the biggest approximate change that we can get in our quantity of interest from removing 2 data points. Now we remove the third largest influence score, and so on. And so before we said we cared about this maximum influence perturbation, what's the largest change we can get by dropping our alpha fraction of the data. And so what we're going to do is we're going to drop as many influence scores as we can until we get to at most 100 alpha% of the data. And what we'll be left with is the approximate maximum influence perturbation. What's the largest change we can get in the approximation by dropping at most alpha fraction of the data? Along the way, we can remember what were the data indices that we dropped to get there. And so we'll call those the approximate most influential set. What were the data points that we dropped to achieve this approximate maximum influence perturbation? So these are exactly the approximations that we saw in that microcredit example from before. And they're what we're going to analyze in the next few slides going forward. So in particular, where we're going next is first we're going to look at some simulated data sets, because there we can completely control the model and how the data is generated, and we can get some intuition about what's going on. And then we're going to look at more very real-life data analyses, all from economics. OK, so let's think about what makes an analysis non-robust, again, to this specific type of robustness. And we're going to start, again, with something super simple, because this is where we have intuition, and so we can compare to our intuition. We'll start with a linear model with Gaussian noise. So here we just have a simple one-dimensional continuous feature xn. We have a simple one-dimensional continuous output yn, and we have a one-dimensional parameter theta. Now we're simulating our data. We're going to simulate it with noise that has its own variance, sigma squared epsilon. We're simulating our data, so we're going to simulate our xn's to be IID with their own variance, sigma squared x. We're simulating our data, so we got to choose theta. We're going to choose it to be 0.5. We're going to make 5,000 simulated data points, and we're going to say that the way that we make our decision is based on the sign of theta hat. So we're going to ask, can we change our decision? Can we flip the sign of theta hat by dropping a very small fraction of these data? OK, now I said earlier that we're going to see that a notion of signal to noise is what this type of dropping data robustness is reflecting. And so we'll talk about a more general version of this later on, but let's see the specific version for this example, because I think, again, we have a lot of intuition with linear regression. So signal is the size of change that we're interested in making. So if we're trying to change the sign in this particular example, we want to take theta hat from its current value to 0 to change its sign. And so that change, or delta, is equal to the absolute value of theta hat. And the intuition here is if theta hat is really large, this should be a relatively easy problem to find out its sign. If theta hat is relatively small, this should be a relatively hard problem. Now, noise in general is going to be an estimate of the scaled asymptotic standard deviation. In this particular case, though, it takes a really nice form. It's about equal to sigma epsilon over sigma x. Why does this make sense? Well, if sigma epsilon is super duper duper tiny, and sigma x is super duper duper big, there is no debate about what theta is. Everybody's going to agree. We're all going to have, a complete agreement about theta, and in particular about its sign. Conversely, if I have the exact same theta, but sigma epsilon is really, really huge, and sigma x is really, really small, it's really, really hard to tell what theta is. This is a hard problem. We're not sure what its sign is at all. So in particular, when signal is large and noise is small, when signal to noise is large, we have an easy problem. When signal is small and noise is large, we have a hard problem. It's hard to find the sign of theta hat. So let's see how this corresponds to dropping data. OK, so what we have here on the horizontal axis is we're changing sigma epsilon. So we're changing sort of how things vary around that line. On the vertical axis, we're changing sigma x. We're changing how spread out the features are. Now what we're seeing here is that when sigma epsilon is very large and sigma x is very small, that is to say the signal to noise is very small, we can drop an extremely tiny fraction of data to change the sign of the effect, the estimated effect. As the signal to noise increases, we find that we have to drop more and more data to be able to change that sign. This analysis becomes more robust. And eventually we get to the point where it's so robust that we're actually away from the area where we even trust the Taylor expansion, that the approximation itself breaks down. At some point it starts reporting it can't find any data points to drop. And again, we're in a region where the approximation breaks down, so maybe we don't trust that entirely. But the point is, we can detect if dropping a small fraction of data suffices to change our conclusions. If we get to the point where the approximation breaks down, that means there was a very large amount of data that we had to drop to change our conclusions, and so we're not too concerned. But if it turns out there was a very small fraction of data that we could drop to change our conclusions, then we can report that reliably. Okay, now the real point here, though, is to note that the sensitivity to dropping a small fraction of data really tracks the signal-to-noise ratio here, that it's reflective of the signal-to-noise ratio. Also, we see that a number of things that are decisive for other types of analyses or other types of robustness are not decisive here. This isn't just picking up misspecification. All of these examples here are well specified, and yet we're seeing robustness and non-robustness. This isn't just reflecting whether we're looking at means or whether we have heavy tails. In all of these cases, we're reporting means. In all of these cases, we have light tails, and yet we're seeing robustness and non-robustness. This isn't just reflecting gross outliers. In fact, in all of these cases, the data points we dropped are very much not gross outliers. Okay, so this is our simulated analysis. Now let's go ahead and look at more real data analyses. I can't emphasize enough how much these are all super awesome studies from economics and awesomely reproducible. Again, I just feel like we could learn so much from this field, at least in terms of reproducibility, so that's very cool. Okay, so first I promised before that we would see that this isn't just reflecting non-significance in the problem. So very famously, there was this Oregon Medicaid study in the US. So there was a lottery in Oregon in the USA where the winners could sign up for health care. I think many of you are from Europe, and so you will find that dystopian, and it is, but that is how it is in the USA, unfortunately. So there was famously a study based on this because it's sort of a natural experiment. So Finkelstein et al. Had this very cool study looking at this natural experiment. Now, there is still this issue of the 21,000 data points were actually survey responders. So there could be some sort of survey non-response bias, and again, that makes us concerned about things like, does dropping a very small fraction of data change our conclusions? Now, this study looked at a lot of different things, and we analyze all of its analyses again in our paper, but I'm just going to focus on one for the moment for illustrative purposes. So they found a statistically significant result that p was less than 0.01 for a positive effect of winning the lottery on a particular health outcome, on a notion of health. Now, this is the kind of thing, this is what gets you in the news. You have this very statistically significant effect. This is very exciting. But we do find in this case that we can drop 10 data points, that's 0.05% of the data, and change the statistical significance here to non-significance. Now, I want to emphasize this isn't 5% of the data, it's not 0.5% of the data, it is 0.05% of the data, so a very, very small fraction. One might think that maybe being Bayesian would stop this kind of sensitivity, or maybe the problem is just using these models like OLS that are too simple, and so maybe if we used more complex models, we would solve this issue. And in fact, these are not the cases we're going to see here. So our collaborator, Rachel Meager, actually has this very cool paper from 2022, where she actually does a hierarchical Bayesian analysis of all 7 randomized controlled trials of microcredit that I mentioned earlier. So this includes all of the data from that one trial, but also a bunch of additional data. She's got this hierarchical Bayesian analysis, which, in theory is this really nice principled way of combining data from, potentially different countries in a principled way. She doesn't just use a standard Gaussian likelihood here. a standard sort of linear regression. She uses very carefully chosen likelihoods and priors based on her economics expertise. I think this is sort of the best we could ever hope for in terms of a practitioner really using Bayesian methods and making their model. But we still find that it's sensitive to dropping a small fraction of data. So we can drop less than 0.03% of the data to change a Bayesian notion of statistical significance. So in particular, whether 0 is in the 95% confidence or the credible interval. And this is now for the microcredit effect across all the countries. So how much is microcredit helping business profits? And we can drop less than 0.1% of the data to change the effect sign, which here is based on the posterior mean. Okay, a few more observations from real-life studies. So it's not just that everything is non-robust. So earlier we saw in our simulated examples that we saw both robustness and non-robustness, but you might be concerned, hey, those were simulated examples. Everything was well specified. Maybe if I had misspecified models, everything's going to be non-robust, but that's not the case. So Angelucci and DeGiorgi 2009 have this nice study of the effects of cash transfers on consumption in poor households. So this, again, sort of comes back to Shakir's talk. There are lots of different ways that we can measure outcomes, that we can measure effects. Here we're looking at consumption instead of something like business profits. So this study had over 10,000 data points in this part of the study. And we find that you have to drop a lot of data to change the results. So remember, we make this observation that we think that a good analysis should eventually change if you keep changing the data. And so here, we have to drop at least 4% of the data to change the conclusions, sometimes as much as 10% or more, to change things like the sign of an effect, the significance of an effect, both of them. And so that seems pretty high. Certainly nothing like the 0.1% or 0.05% that we saw earlier. Finally, I mentioned that removing outliers isn't a panacea here. So this is considered a robustification procedure for, again, other types of robustness. So people who are worried about things like epsilon contamination. But in this case, it's not going to just solve our concerns about robustness. So Angelucci and DeGiorgi 2009, what a cool study. They look not just at consumption in poor households, but they also look at this other idea of a spillover effect. So if poor households in a village are given microcredit, do the non-poor households benefit as well? So that's the idea of the spillover. So in this case, the original analysis actually does this kind of pretty standard, actually, robustification procedure, removing the largest responses in advance, some kind of trimming. But we find that even if you ignore those largest responses that they removed, you can still remove just 3 data points out of, in this case, over 4,000 data points, and change the statistical significance. Okay. So let me just spend a little time now talking about a little bit of theory. So some concern that I think we might have in general in machine learning is that, hey, we run on a few examples. We have our few empirical examples, but is this something that we expect to be true in general? Do we expect to get the same results, in general? Were these like cherry picked, or did we just get lucky with our examples? And so now let's spend a little time thinking about, do we expect our approximation to be accurate in general? And do we expect that we can make these interpretations that we made before, the signal-to-noise ratio in general, in other cases? Now, I said earlier for the accuracy that we have this really nice check at the end, that we tell you the data points that were problematic. And so you can just drop them and check after the fact that you got the same change as was promised. And in fact, we do that check in the paper, and we very much recommend that anybody do that check in general. They don't have to rely on our theory. But of course, we're still in the situation that it wouldn't be a really great check if it turned out that every time somebody actually dropped our data points, that they got a totally different result than what we had expected. We'd like something that suggests to us that we expect to get good approximations. And so that's what we're going to focus on in the theory. So let me just give you a little bit of a sketch of the theory that we have. So what are we trying to do? We're trying to say that our linear approximation for dropped data is close to if we actually dropped the data. Well, what does it mean to be close? What's a natural scale for this problem? One potential natural scale is to compare it to if we actually dropped the data versus if we didn't drop the data at all. Certainly, we'd like our approximation not to swamp this difference. Now, we have to be a little bit careful because the thing that we're actually doing at the end of the day is taking the worst case, W. So out of all the cases where we're dropping an alpha fraction of the data or less, we want the W that's going to give us the biggest change. And so we want to take, what's the worst case W here? And so we're going to bound these quantities. And in each case, we get a computable constant times some function of alpha. So remember, alpha is the fraction of data that we're dropping. We're thinking of it as being very small. Now, if you're used to thinking of asymptotics as n gets large, it might look like this is backwards. But remember, we're thinking of alpha as being very small. So when alpha is very small, alpha is actually going to be smaller than square root of alpha. And so we're getting a bound on our approximation that's smaller than the bound on the difference between dropping the data and not. So just to summarize here, we say that under very smoothness and regularity conditions, the bound on the error in the linear approximation shrinks faster than the bound on the difference due to dropping the data as alpha goes to 0. Now, I can't emphasize enough that there are still very important limitations here that are basically being somehow subsumed into that smoothness and regularity conditions. This is a local approximation. So if you don't think a local approximation is going to be a good approximation, if you think that you have a lot of interactions that aren't captured by first-order Taylor expansion, then this is not going to be a good approximation. But of course, we've seen in a variety of real analyses that in many cases this will be, in many cases very much of interest in applied analyses. Okay, so let me turn to the interpretation. So let me just talk a little bit about interpretation of our theory here. So remember I said that there was a more general notion of signal to noise. We saw in a particular example in the linear case, but now let's talk about the more general example. Now remember, what we were trying to do was we were saying, okay, for this worst case W, let's call it W star now, what's this difference between our linear approximation and our original analysis? So this is approximating what's the difference we could get, the biggest difference between dropping data and our original analysis. And we're going to compare that to some delta. This is going to be the size of the change that would reverse the conclusion. If this difference is bigger than that change, we're worried. If it's not, we're not worried. And it turns out we can decompose this difference into a noise term times a shape term. The noise, as I super briefly mentioned earlier, is a consistent estimator of the standard deviation of the limiting distribution of the quantity of interest. And the shape, for our purposes now, is just something that converges to a non-zero constant. And so if we just rearrange this equation here, we find that checking for robustness is the same as checking whether signal to noise is greater than or equal to, less than or equal to some constant. So literally, we are checking for a signal to noise ratio in the problem. And that is what our method is reflecting. And there's some really cool corollaries we can get out of this observation. So one of them is, as n goes to infinity, all of these quantities go to constants. And so our AMIP sensitivity doesn't vanish. And I actually think that's a really nice contrast to p-values and to standard errors. So typically when you're testing for statistical significance, you're going to use a standard error. As n goes to infinity, that standard error is just going to go to 0. But we know we're working in a misspecified world, that an effect size isn't naturally, or that we're not really getting stuff going to 0. And so I think this is not really reflective of something we want, that just no matter what you do, your standard error is going to go to 0. Because in your misspecification, you're always going to be off slightly from 0, and so it's going to look like you have something that's statistically significant just by the math working out. Okay, and so a corollary here is that statistical non-significance actually becomes AMIP non-robust as n goes to infinity. Okay, so let me just conclude. So we present a way to check there's a very small fraction of the data that you can drop to change your substantive conclusions, an empirical and theoretical analysis of its properties. Our paper is up on the archive. The author ordering here is alphabetical because we are deferring to our amazing economics collaborator, Rachel Meager, but I really, really want to highlight the amazing work of, again, Ryan Giordano and Rachel Meager. They've taken just a huge leadership role in this paper and done fantastic work. The code is up here at Ryan Giordano's GitHub. ZAM influence stands for Z estimator maximum influence, which hopefully you now see the relationship to what we've done. Michael, a super cool person who is totally not us and not related to us, has written this cool blog post about how our method flags p-hacking, which is, I think, a really nice observation. And Ryan has a follow-up blog post about sort of why that is and what's going on there. And then finally, I just want to make a couple of quick points. So one is that I really hope nobody sees this as some kind of gotcha for the economics field. I think quite the opposite. The reason that we were able to run these analyses is because economics is so reproducible. That is a step zero that is very much missing in many applications of machine learning. So we actually have this paper in Nature Matters Arising 2020 pointing out a medical AI application where there isn't code, there isn't enough information to reproduce the code. And I think medical AI is an area where we really care, again, about results. And so, how can we make things get to this reproducibility stage where we can then make checks like this? And then finally, I'll just point to our Science Advances 2023 paper where we point out how really this check just fits into a broader ecosystem of checks, that there are really many things that we want to be checking in our analyses. Again, this is just one of them. It's certainly not an end-all be-all. Thank you so much.